I bet you have wondered about negative temperature, right? It sounds like something from science fiction, or maybe just a misunderstanding of how cold things can get. But here's the kicker. Physicists have actually achieved temperatures below absolute zero, and these states are considered infinitely hotter than anything we experience normally. It is a mind-bending concept that turns our everyday understanding of hot and cold completely upside down. Let us demystify this together really quickly. When we hear negative temperature, our first thought is usually colder than absolute zero, but that is where the intuition misleads us. Absolute zero, or 0 Kelvin, is theoretically the coldest possible temperature, where all particle motion stops. So, how can something be colder than absolute zero and simultaneously infinitely hotter? This is not about how cold a freezer can get. It is about a fundamental redefinition of what temperature means. First, let us nail down what temperature normally is. In simple terms, temperature is a measure of the average kinetic energy of the particles within a substance. The hotter something is, the faster its atoms and molecules are jiggling around. The colder it is, the slower they move. It is pretty straightforward for the everyday world. Now, absolute zero. This is the theoretical point where all motion stops, and particles have the absolute minimum amount of energy possible. It is a fundamental limit in the universe. We can get incredibly close to it in labs, but reaching it is a different story thanks to quantum mechanics. It is the bottom of the temperature scale, the ultimate cold. To understand negative temperature, we need to think about energy states. Imagine energy as rungs on a ladder. Each particle in a system can occupy a certain rung, representing a specific energy level. The lowest rung is the ground state, with minimal energy, and higher rungs represent higher energy states. All particles are constantly trying to find their place on this ladder. At normal, positive temperatures, the particles in a system follow what is called a Boltzmann distribution. This means most particles occupy the lower energy rungs of our ladder, and fewer particles occupy the higher energy rungs. It is like a pyramid, wide at the bottom, narrow at the top. This is the natural stable state for energy distribution. The key is understanding that temperature, in a deeper sense, describes the distribution of particles among these energy states. A positive temperature means there are always more particles in lower energy states than in higher ones. This is why heat naturally flows from hotter objects to colder ones. It is a movement towards a more even or less energetic distribution. Think of it this way. If you let a bunch of marbles on a staircase, they would naturally settle on the lowest steps. To get them onto higher steps, you would have to put energy in. In a positive temperature system, particles are constantly trying to fall to lower energy states, releasing energy as heat to their surroundings if they can. Now, imagine if we could somehow force most of the particles to occupy the higher energy rungs, with fewer particles on the lower ones. What if we flip that distribution completely upside down? This is not something that happens naturally. It requires a lot of clever manipulation and energy input. This, my friends, is precisely what a negative absolute temperature state is. It is a system where there are more particles in high energy states than in low energy states. It is an inverted population, completely contrary to the natural order of things. It is like having more marbles on the top step of the staircase than on the bottom. It is crucial to stress, this is not colder than absolute zero. In fact, you cannot pass absolute zero to get to negative temperatures in the traditional sense. You approach absolute zero from positive temperatures, and then, through a burst of energy, you essentially jump over infinity to the negative scale. It is a different domain altogether. The defining characteristic of a negative temperature system is this inverted population. Instead of the familiar pyramid where most particles are at the bottom, we have a Toffevi structure. Imagine all the energy levels packed at the highest possible states, leaving the lower levels relatively empty. This is a state of extreme energy. What is fascinating about this is how we achieve such a state. You do not get negative temperatures by simply cooling something down. Instead, It involves carefully manipulating the energy of particles, often using laser light or strong magnetic fields, to pump them up into higher energy states faster than they can decay back down. This inverted population is inherently unstable. Just like those marbles on the top steps of a staircase, they want to fall back down to the lowest possible energy states. They are in a highly energetic, non-equilibrium situation. This desire to return to a normal distribution is key to understanding its hotness. So, why is it considered infinitely hot? The simple answer lies in energy transfer. If you bring a system at negative, absolute temperature into contact with any system at a positive temperature, energy will always flow from the negative temperature system to the positive temperature system. This is the definition of hotter, giving away energy. Think of it this way. The negative temperature system has such an extreme overabundance of high-energy particles that it is desperate to shewood that energy and get back to a more stable, positive temperature distribution. It is like a spring wound incredibly tight, just waiting to release all its stored potential. This leads to a constant flow of energy out of the negative temperature system. No matter how hot a positive temperature system is, the negative temperature system will always be hotter in the sense that it will transfer energy to it. It always acts as the energy donor, driving the change. Here is a simpler analogy. Imagine a crowd of people. In a normal positive temperature scenario, most people are on the ground floor and only a few brave souls are on the top floor of a skyscraper. This is the natural order. Now imagine a negative temperature scenario. Through immense effort, you have managed to get almost everyone onto the very top floor, leaving the ground floor nearly empty. This is an incredibly unstable, high-energy state. If you then open a door between this toffee-heavy building and a normal ground-heavy building, what happens? People will immediately start flowing from the toffee-heavy building into the ground-heavy one, eager to find lower, more stable positions. That flow of people is like the flow of heat. The infinitely hot part comes from the mathematical definition. As a system approaches absolute zero from positive temperatures, its temperature value approaches zero. But when you cross over to a negative temperature, the mathematical formula effectively wraps around, and the magnitude of a negative temperature starts from negative infinity and goes towards zero. So, while a negative temperature value like 1 Kelvin seems close to 0 Kelvin, in thermodynamic terms, it is actually hotter than any positive temperature. It is the most energetic, least stable state a system can be in, as all its particles are packed into the highest available energy levels. It feels counterintuitive because our everyday experience of temperature is always within the positive range. We do not interact with systems where energy distributions are inverted. You will not find negative temperature coffee or ice cream because those systems quickly revert to normal positive temperatures by giving off heat. These exotic states are achieved under very specific laboratory conditions, often in extremely dilute gases where only certain energy levels are accessible. The systems used are usually atomic spins or very specific quantum systems, not bulk matter like water or metals. What we discover is that negative absolute temperatures are not about being colder at all. They are about an extreme concentration of energy that makes the system unstable and eager to transfer that energy to anything else it touches. It is a state of immense energy potential. So, what are the implications? These negative temperature states are not just a theoretical curiosity. They have practical applications in fields like quantum computing, laser technology, and the development of highly efficient heat engines. Understanding these states pushes the boundaries of thermodynamics. Ultimately, the point is that temperature is a more nuanced concept than we often assume. It is not just about kinetic energy, but also about the distribution of energy within a system. And when that distribution gets flipped on its head, some truly fascinating and counterintuitive physics emerges. The biggest lesson here is to challenge our assumptions, even about something as fundamental as hot and cold. The universe has a way of surprising us with complexities that redefine our understanding of basic principles. Negative absolute temperature is a perfect example of this. The core idea is that negative absolute temperature is not cold. It is a state where a system has more particles in high energy levels than low energy levels, an inverted population. This makes it thermodynamically hotter than anything positive because it will always transfer energy to a positive temperature system. It is a spectacular demonstration of how extreme conditions can twist our everyday concepts into something truly extraordinary.